So yeah, I'm going to talk a bit about a journey we've been on to build a Postgres data warehouse using DuckDB. So I've been sort of working quite intensively in the Postgres space for the last 10 years, 11 years actually. First at a company called Citus Data that built one of the first commercially successful extensions. It was acquired by Microsoft. And throughout the time, I've built various PostgreSQL extensions. There's PG cron, a job scheduler. Recently open sourced PG DocumentDB. I created that a while ago at Microsoft as a MongoDB implementation on top of Postgres. But last year, me and two longtime colleagues decided to start a new project and also get into the DuckDB space. So but most of the past 11 years have been on this Citus project, and it was basically distributed Postgres as an extension. And when we started that, we kind of thought, okay, we might go into the analytics space. It's a long time ago. The Hadoop was still a big thing. It was very slow. Spark wasn't really reliable yet. Impala was very limited, kind of okay though. But what we found in our startup journey, it was easier to go into, or more effective to go into an area where Postgres already had a foothold, such as being the operational OLTP database for software as a service companies that needed to scale out. And also for time series data where you do some sort of simpler pre-aggregation in the database. But probably throughout those 11 years, 1 in 4 people who came to us were actually looking for a Postgres-based data warehouse. So we knew this was a thing people want. But the challenge is traditionally the database world has been split in these two factions, the OLTP faction and the OLAP faction, and they don't really talk to each other very much. But they sort of on the surface look the same. They have SQL, they have DDL, DML, transactions. The thing is that the OLTP databases like PostgreSQL, they focus on high query rates, high rate of updates and inserts as well, with very low response times, like milliseconds. For user-facing applications, lots of concurrent users. Whereas OLAP databases, they focus on scanning a lot of data very quickly. The number of queries per second is not usually very high, but the amount of work an individual query does is pretty high compared to OLTP. And this is usually more business-facing. And these databases, both of these databases tend to be pretty important, deal with a lot of data, a lot of transactions, and they are optimized to the extreme. So they have very different architectures. OLTP databases typically have a row-oriented architecture, so you insert a row and then the next row comes after that. And then the database is optimized for finding a small set of rows using indexes. And then when it gets a row, the executor takes that row, and there might be multiple expressions in the where clause and the select clause. So it evaluates the first expression and the second expression and the third expression, and it goes to the next row. And so when this happens, there's a lot of CPU instructions kind of wasted on just calling the same function over and over again, switching between functions. And the CPU caches are not used very effectively. There's a lot of allocations, there's a lot of memory being moved around. So this is fine if you're just looking up 10 rows, but if you're scanning like a billion rows, this starts weighing in pretty heavily. So analytics databases are optimized differently, where they typically use columnar storage. So a block of values from the same column are stored together, sometimes with compression. And then the query engine can take a vector of values and evaluate an expression on each value in the vector. And so this avoids a lot of this context switching between different functions, which already speeds things up. It makes better use of the caches. And then the CPUs often have instructions that can process a lot of values at the same time in one instruction. And so this can often be already 10 times faster than what the OLTP databases are doing. And then the analytics databases are also much more optimized for query parallelism. Postgres has parallel query, but it's bad. It's not really bad, but it's definitely a lot worse than DuckDB. And if you zoom in, you'll find actually that every little detail of the database architecture is optimized differently. And so this is why these are usually very different projects. You just have to focus on very different things. But now we have DuckDB and we have Postgres, and they're kind of more similar to each other than a transactional database and an analytical database have ever been. They focus on a single server. They have the same SQL dialect because DuckDB started from the Postgres parser for its initial implementation. So most Postgres queries will just work on DuckDB. Now DuckDB made much nicer SQL. Postgres not yet, so that's unfortunate. But and DuckDB is an embedded database system, Postgres server based. So you could embed DuckDB into Postgres. Now, of course, Postgres doesn't have a plug DuckDB in here feature, but it has a very comprehensive extension API. So you can build these extensions, plugins that change the behavior of Postgres to let DuckDB do some of the processing. And DuckDB also has extension APIs, so you can make it more amendable to being integrated like this. Now, why would you actually do this? Should you do this? So one term that often comes up is HTAP. Could you then run your analytical queries directly on your operational database? I've very rarely seen companies really wanting to do that because, well, of course, there's the resource management question. If you're actually talking about the same physical server, you probably don't want to do that, but okay, you could have a replica. But the analysts and the application developers usually work in different environments with different tools. The analysts want to do data transformations, create views, which the application developers don't want. They want a clean, nice, reliable database. And the analysts want to combine data from many different sources, not just one operational database. So separation between analytical and operational database is kind of a natural thing. So why would you want this? Well, one of the things is we often see companies just using, by accident, Postgres as a data warehouse. They do their analytics on Postgres, and it's really slow at some point. Like they started that way because it wasn't slow in the beginning, but at some point it became very slow. And then it's actually quite painful to migrate to another data warehouse because few things are as versatile as Postgres. They might be using geospatial extensions in Postgres, which do a lot of things. There's also very interesting patterns you can have when you combine a transactional engine and an analytical engine. For example, you could still have regular tables where you can do fast inserts, but then you could periodically move the data into an analytics optimized table. And so that sort of eliminates your whole ETL pipeline. I can just use this as a log for collecting telemetry. You can just fire at the database and it goes into my iceberg table, for example. And you can create materialized views from your database. Postgres is very good at serving queries on materialized views with indexes. So you can basically simplify your stack. You go from having lots of tools and glue code to maybe we can just mostly use Postgres and DuckDB. And of course, still other tools like dbt and SQL Mesh, those tools are still very useful. So we built an implementation of this at my company, Crunchy Data, which we very boringly called Crunchy Data Warehouse. And we basically built it as a feature of the existing managed Postgres service. And so we didn't change Postgres, but we used extensions to add the notion of an iceberg table and a data lake table that queries existing files into Postgres. And we find it's often like just 10, sometimes 100 times faster for analytical queries when you're using these tables than when you're using on the same machine the Postgres tables. We also added some like caching layer. So we store the iceberg tables in S3, of course, because that's where you store iceberg tables. But then we find it's nice if you sort of automatically cache the files on local disk because you can get much better response times for a lot of cases. So we had the experience of building this one super complex extension, Citus, over many years. And there were certain aspects of that we didn't like. So we kind of went for an architecture where we have lots of medium-sized Postgres extensions. And this also allowed us to write some of them in Rust, some of them in C, some of them are open source, some of them are still closed, but might be open source in the future. And so we found that to be a useful pattern as well. And so what extensions can basically add functions and types into Postgres. They cannot really add new syntax, but they can change the behavior of existing syntax. And so one thing we really liked in DuckDB is how super straightforward it is to query a file, like from a URL. You just select star from URL, right? Now that syntax isn't easily replicable in Postgres via an extension. because Postgres, like the parser already kind of wants to know which column names there are and column types, and the parser isn't very extensible. So we figured we should have a table, like when you want to read a CSV file from S3 or from the internet, there should be a table. But we didn't want to ask users, like, what are all the columns, the column names, and the column types of this table? Now, fortunately, we figured out that Postgres apparently allows you to create a table without columns. It works. I don't know why you'd ever want to do it. So we can use an extension to redefine what that means and say, okay, if you create this foreign table without columns, we'll look at this URL. We'll ask DuckDB, what does this file look like? Because DuckDB is really good at sniffing CSVs. So it'll tell us the column names and the column types. Now, if it's a Parquet file, then it might also contain structs and maps. And Postgres doesn't really have structs and maps, so then we generate some types on the fly, composite types in Postgres. Now then when you query that table, we sort of try to delegate as much of that query to DuckDB. But yeah, the query we run on DuckDB is not necessarily the same as the query that you ran. For example, the table name will be replaced by the relevant read function, read CSV, or read Parquet, read JSON. And then not all of the functions in Postgres exist in DuckDB. So if you use the date bin function, for example, that doesn't exist in DuckDB, but there is a time bucket function which does pretty much the same thing. So there's a lot of rewrite rules for certain Postgres functions, and operators use a slightly different one in DuckDB. For example, also the division operator works a little bit differently between DuckDB and Postgres. So we change all that sort of under the covers. And so, yeah, the Postgres query planner is very extensible. So for the whole query, we can just generate a very alternative plan and do something completely different than what Postgres would normally do. So if we see a query that can be fully delegated to DuckDB, we'll do that. If not, because maybe there's functions that, like user-defined functions that are only in Postgres, what we'll try is we'll sort of use the hooks in Postgres to start from what I think of as the inside of the query, the scans of the individual tables. So that's where the Postgres planner starts. It looks at, oh, for this table, can I do a sequential scan? I could do an index scan. And then it asks extensions, any other scans you can think of? And then the extension can also say, actually, don't do any of your scans, do my scan. And that's where we can, for example, decide if there's a set of filters where some of them can be done in DuckDB, but some of them has to be done in Postgres, we can generate a scan that does that. But what we ideally want is to go as far out as possible. Like if you join two CSV tables, can we do that in DuckDB? If you do a group by, can we do it in DuckDB? And there's a lot of rules here around which functions are available and which query constructs work in DuckDB, because, for example, in Postgres, you can have a set returning function on the select. In DuckDB, you cannot, except when it's unnest, but then unnest cannot be used in the order by. So there's a lot of subtle incompatibilities that we need to kind of work through. And in the end, we get this query plan that sometimes actually does multiple queries on DuckDB for a single Postgres queries, and then has other Postgres execution nodes to combine them. So this is for just querying like files that are already in the data lake. So for storing data into your data warehouse, we implemented Iceberg. And the basic idea with Iceberg is it's a collection of Parquet files in S3 with some metadata files that describe which files are currently part of the table and what the current schema is. And there's like a top level metadata file which describes like one version of the table. And to know what the current version is, you need to kind of consult a catalog. Now, the catalog is essentially a database with an API. And in fact, the catalog can just be a Postgres server. In fact, because we are a Postgres server, we don't need a catalog. We can just be our own catalog. And other applications can talk to us to get the latest version. So that's kind of nice because, for example, one of the things we wanted to do is be able to do point-in-time recovery. So you kind of go back to take your backups, you go back in time, and now a Postgres server wakes up with older versions of all the tables, including the catalog table, which now points into a different like an older metadata file. But we can make sure that that file and all of the file it points to are still there. We kind of keep them for 10 days. So that's something we really liked about Iceberg, that we could sort of align the Postgres timeline with the data lake timeline. So for Iceberg tables, you can just create a table using Iceberg. When you do that, again, the extension gets called. We write the necessary metadata files into S3. So we actually implemented Iceberg from scratch. So it was kind of fun. And then you can do inserts, you can do triggers, you can do constraints, you can do modifying CTEs. And so if you do an update, we'll use DuckDB to find the rows that match the filter of the update. And then we use the file name and the file row number option in the read parquet function. And Iceberg has this notion of a position delete file, which is basically a file of file names and row numbers that have been deleted from the existing parquet files. So we can use that to generate a position delete file, and the new values of the rows go into a new parquet file, and then we update the metadata and the catalog, and then commit our update. And then after that, if you query the Iceberg table, so again, we'll do this kind of planning process, but now when there's position deletes, we'll basically filter those out where, like by doing a sort of anti-join with the position delete file. So again, we ask for the file name and the row number, and we ask for the rows that are not in the position delete files. So this is similar to what the DuckDB Iceberg extension does internally, but we don't directly use that because we needed rights. And it was sort of nicer to implement it ourselves because we could do a much smoother integration. For example, we also do compaction automatically in the background. So if you do a bunch of small inserts, you get a bunch of small parquet files. At some point, every 10 minutes, those get kind of compacted into a bigger parquet file. And that also just uses DuckDB. So just a quick recorded demo. So this is an example I discussed earlier of you could have an insert queue. So we have an Iceberg table for storing events. We just load some data into it. I think I was actually running this from my laptop, so the S3 latency is a little bit high. But because we cache the files locally, like queries on the Iceberg table are actually really fast. But then inserts always are a bit slow. They're usually about 1 second in the managed service. So what we can do is we can create an insert queue, just a regular Postgres table. We set up a periodic job that every 5 seconds takes all the stuff from the table, inserts it into the Iceberg table. Now we can insert into that queue in under a millisecond. And then because it's kind of being flushed in the background, we've already added the rows into the Iceberg table. So that's a very nice pattern that's normally requires a big ETL pipeline, but here it's just sort of automated and transactional. So yeah, DuckDB experiences, great performance. Read functions are very versatile. We love that. Wildcards are great. Postgres compatibility is actually very close. Extensibility, concurrency, and the bugs get fixed. Well, Mark's not here, but thank you, Mark. What could be better? So for complex queries, we sometimes, like Postgres users, like to write very complex queries with lots of CTEs and joins and unions. And sometimes, like we do run out of memory. The disk spilling doesn't quite save us. The parsing for text arrays and structs is a bit broken. If you put a array of text with some commas in the strings into a CSV file, it'll be messy. Parquet pruning sometimes could be a little better. Like if we do where x equals 3, things are great. If we do where x equals 3 or x is null, things are less great. And then I think what we hear the most from users is like they want more Azure, GCP, and S3 feature support, like customer managed keys, Azure writes, GCP, alternative authentication mechanisms. Query interrupts could be a little better, like if there's a large list operation, DuckDB doesn't check for interrupts. But I think those are things we'll actually try to also do some contributions in. So yeah, in summary, you can build a data warehouse out of Postgres using DuckDB, and then you don't need to go and build a new query engine and figure out how to combine all the operational database trade-offs with the analytical database trade-offs. You can actually just sort of glue them together. And it has the potential to significantly simplify certain data stacks. So I think we're the first to sort of launch a product in this space, and we have a bunch of customers in production now. There's also other projects under development, PG Analytics, PG DuckDB, and PG Mooncake. So those also look very promising. All right, any questions or straight to drinks?